Hello. After my one-way speed of light Veritasium response, part 1, there's one person that has asked a question, put together a scenario, and I think after some clarification, I've understood what he's trying to do. Essentially, we've got four clocks, A and B on one side and C and D on the other side, and they are 1 kilometer apart. And they synchronize one pair of the clocks, but they don't synchronize the other pair of clocks. So this is the way I'm kind of picturing it. We've got a guy over at this end looking at his two clocks. They both read 10, t equals 10. And this guy over here, these are random kind of times. They've both got these two clocks synchronized to each other, but not necessarily with the one across the field. And it's 1 kilometer across the field. So let's say this guy, he has clock A set up so that he can push a button on it, and when that button is pressed, it resets to 0 and sends a signal to clock C. Okay, they've both measured this. They've already measured the distance between these two places, so they know that distance equals ct, the speed of light times time. So the amount of time that should pass is distance over c, which is 1,000 meters, divided by 3 times 10 to the 8th meters per second. And that comes out to be about 3.33 microseconds. And since these clocks are already set in 3.3 in microseconds, these aren't seconds, they're microseconds. So clock C resets itself to 3.33. Okay. And then the returning signal comes in, and when it is received, when this guy pushes the button to make that one be 3.33, it returns the signal. Actually, it doesn't even need to hit a button. If this guy can read the clock, then that signal, the appearance of reading the clock, will return at the same time. So when his guy sees 3.33, assuming the speed of light is the same, this clock should read 6.66. However, this clock should also have gained 6.66 seconds, so it would read 16.66. So at that point, clock B will not be synchronized. The rate at which this has gone from 0 to 6.66 will be the same as the rate at which this has gone from 10 to 16.66. That's my understanding. I guess I could round that to 6.67 since it would round up at that point. But then, and then the signal will come back here, and by the time it reaches back to there, another 3.33 another 6.67 microseconds would have passed for him. This one, I should have made that 30, so it would have been easier to work with. But anyway, yeah, so 3.33, etc., etc. This gain would be at 10, and this one would be at 35. So you've got those two clocks, and the rate of change for the two clocks is the same, but they would have different readings. So if I put this into a space-time diagram, it would be, let's say AB was over here. It would have been, A would have gone, they both, where did we start them? We start them at 10, right? So 0, 0. We'll put both A and B's time reading over here, and 10, 0, no, 0, So 9.99, 9.99. A gets reset to 0, B stays at, just keeps going up at 10. Then the signal goes from A to B. These guys both read. Can I make it? Can I change it? Let's actually make them. Let's say they had 30 on them because it'll be easier to work with 30. So D goes up to 33.33 and C gets reset to 3.33 at that point. Signal returns and B reads 16.67 and A reads 6.67. But there wasn't any, so there was a synchronization procedure done here, and there was a synchronization procedure done there. But this guy can actually tell, or this guy could have at any point said, I'm going to synchronize my clock to that one because I can see the reading of it. It says 10, so I'm going to add 3.33 and set my clock to 10.33. So he could have set clock D at any time to 10.33 and it would have been synchronized with clock B. Okay, so let's say you draw all of those events on so that they are represented on a bunch of cards. You have the x coordinate going this way and the y coordinate going this way, and then you just shift those cards like this. So nothing has changed on the no images have actually changed on the cards, so you've still got all of the readings, all of the synchronization procedure still represented, but now instead of being represented by this line and this line, you've caused the speed of light to increase up this way and then maybe come this way on the way back. You might. So you've changed the round trip speed of light, but you haven't changed any of the actual events in the space. And so long as your synchronization procedure doesn't actually affect any of the images on the cards, doesn't change your route through the cards. Like say, if instead of just synchronizing his clocks, he decided, I'm going to change the direction of the clock. I'm going to accelerate the clock and send it maybe over in this direction. What happens then? Well, here's the problem. Right now we're imagining a situation where vertical lines in this diagram represent staying in the same place. With this particular operation, there is no way we can make that slope as steep as we want with this operation. We can take that line and make it much steeper, but there's no way to actually turn it into a vertical line. On the other hand, if we did this and tilted it that way, it would be quite an easy matter to turn this into the straight line and make the speed of light change in either direction. So once you do that and make the clock go up in a straight line, now you're having a different problem. The speed of light is actually going to be skewed so that we've actually slowed it down coming this way and sped it up coming this way. So here I've drawn it, so here's a card, a card, a card, a card, and they come down kind of like this on either side. And you can see the clock says t equals 0 here. This clock says 3.33. This clock says 6.67. This one says 10, 13.33. So these are the two clocks that have been kind of pushed, that have been, let's see if I can do this again. I should basically taken and I've skewed them this way, but we've made a person be traveling just straight in, be stationary in this diagram, which would not be the same point on the cards. But as far as this guy is concerned, the speed of light actually would be different in the two on the way from this clock to this clock. It is going a shorter distance, and then on the way back, it's having a longer distance. On the way back this way, it's having a shorter distance, and on the way back, it's having a longer distance. And nothing's changed about the cards. The card has stayed the same width, so it's the same amount of time for, as far as he's concerned. These are the actual times that he measures too. So he says, no, the speed of light is different in one direction than it is in the other direction. But then he goes about and he says, hey, you know what? Since we're here, let's go ahead and set up the Fizeau-Foucault apparatus in our frame, and I'll decide to prove it. And I set up my own clock here and my own clock here, and he does the measurements. And he goes, and guess what? He finds that when he does the measurements in his own frame, the speed of light is the same in both directions. So nothing actually impossible has happened. It's just that this is not the correct operation, because this one preserves those readings, but it does not maintain the proper speed of light. We need an operation that does both. It preserves these readings and it gives the same speed of light in the new reference frame. And the one that does that does a little bit of both. It does this, the skew in this direction, but it also does this at the same time, backwards, I guess. This in the other direction, and that is called the Lorentz transformation because it keeps these two slopes the same, and those two slopes are at the speed of light. And so as long as it doesn't change those slopes, then it doesn't change.